Okay, so homework for next Tuesday. Our exam is next Wednesday night. So this afternoon, it's already actually up. The folder for Exam 3 study resources is there. I just need to move it to the top. But it'll be available and easy to find this afternoon. So you don't want to wait till Tuesday to start studying for your exam. Okay. Homework for Tuesday. You've got 6 written problems from the text. We'll turn in Tuesday in class, and then on reading associated with that, and then the next 2. So tonight you have sets 1, 2, and 3 are the cutoff is tonight at midnight. I'll show you that in a second. Weber. I can show you right now. Okay, so. Sets 1 through 3, your cutoff is tonight at midnight. As you see, it says right there, the 20th at 11:59 p.m. 1 and 2, all the problems are extra credit, but they're all very helpful for the third exam and the final. Okay. The optimization, you're required to do 3 of the first 9 and 1 of the last 3. So 4 total problems you're required to do. Any of the rest of them are extra credit. All of those are due tonight. And then the next 2 sets, 4 and 5, those are due Wednesday at noon. So that's not 11:59 p.m., that's 11:59 a.m. next Wednesday. And that was so that you could have answers and feedback for your studying that night for the test. So I wanted to have those due before the exam with some time for you to get some feedback from the answers. Okay? So that's all extra credit, okay? 4 and 5 are all available for extra credit. But again, great practice for what you're going to be tested on. Questions on web work? Questions on web work? Or next Tuesday's homework? Okay, so let's jump back into it. We were doing implicit differentiation. Okay, so here's an equation. 75 sine of x minus y minus 3y squared x equals e to the xy minus 67. Is y a function of x? Is y a function of x? Certainly not. You're looking at some examples here where given an x value, you're getting more than one y value. Okay? And if we were to try to solve that for y, it looks like it's impossible, right? X and y in this equation are so intertwined by sine and by e to the xy, it would be literally impossible to solve this so that y was a function of x. But as we talked about last time, if we pick a point on here, for that point, does it make sense to talk about the rate of change of y with respect to x? Would it make sense to talk about the rate of change of y with respect to x? Which is about what? Given what? The rate of change of y with respect to x means given. Has anyone learned something this semester? Given
a change in x, the change in y.
Why don't you have a seat first? But you're doing great. Given a small change in x, right? Given a small change in x, change in y would be that many times that change in x, right? So it makes perfect sense, isolating around that point that I've drawn, to talk about the rate of change of y with respect to x. So that's what we're after here. We've got this equation that gives us, what, a set of points. Let's see that set of points a little more clearly. What does it mean for a point on that curve? What does it mean for a point on actually any one of those curves, right? There's multiple curves here. Some are isolated loops, right? What does it mean for any point that I pick on that curve? What do we know? So that point that I just picked, if it's on that blue curve, then what? Yeah. Right, exactly. Well said. If I took the x and y coordinates of that point and put them into that equation, it would make it true. You'd get the left side would equal the right side. And so that's what's true for every point on these curves, right? Because you're looking at a collection of points. What about this point? Or this point?
No.
Take the x and y coordinates, put them in, what will happen? You get a different value on the left from the right. It won't be equal, right? It won't be equal. You get a different value on the left than you get on the right. Okay? So that's how that equation and what you're looking at are mathematically the same thing, just different representations of what? A set of points. A set of points that make the equation true, and a set of points in the xy plane. Okay, so let's find, we want to find dy dx for this really cool graph, right? It's the coolest graph you've seen all day, I'm sure. Okay, so what do we do? So what do we do to do this, right? So we're gonna think about taking the rate of change of the left side and the right side, and we're gonna apply all the same rules we learned in the mastery test. But then we're gonna keep in mind that kind of somehow y is a function of x. It's not really a function of x, right? But we're gonna pretend that it is in order to make this work, okay? So it's implied. It's implied that y, in any local area, we could say y is a function of x, right? In any local place, we could say y is a function of x. So that means anytime we have a y, and we take the derivative of it, or an expression of y, like y squared, what are we going to need? We're going to need the chain rule, right? Because if that y squared is really, we think of it as a function of x squared. So we're going to need the chain rule. But this time when we do this example, we're not going to change them all to f of x's for convenience. Just remember that whenever you write a y down, you see that and you think that, oh, that's some function of x. And so that's how we have to operate in the rules of the derivatives, right? So here we go. Rate of change of 75 sine would be 75 times cosine. Are we done? Okay, so we got chain rule now, right? So times the rate of change of x minus y, which is 1 derivative of x minus, yeah, so we can say f prime, we can say dy dx, or we can say y prime. Let's just go with y prime. Now I'm spacing this out to make a point here, so it's going to help us, okay? All right, so now what about minus 3? So that's the derivative of 75 sine x minus y. And so what about minus 3y squared x? So that's going to be, what do we have there? What's the structure of that? Product. So we want to use careful. So you want to do the derivative of the first. So what is the derivative of 3y squared? I agree with 6y, but y is a function of x, so we need chain rule, right? We need the chain rule, so we need y prime. See that? Y is in terms of some function of x, or that's implied anyway. That's implied. So by the chain rule, we would need the derivative of the interior function, which is y prime. Okay, then minus 3y squared times rate of change of the second, 1. So there's our product rule. Okay, because it's a function of x. We could write it as 3f of x squared times x. Now, what's the derivative of that? F of x, maybe it's square root of x, or sine of x, or x to the x cubed plus natural log of x. How would we do the derivative of that? Well, it'd be 6 times f of x to the first times the rate of change of the interior. Is it better?
And then x would just become 1. And so 1 times that would be that. But what's with the negative? Why are we minus? It's not a minus 6y times y prime minus 3y times 1. Why wouldn't you just have, why wouldn't it be?
Yeah, so this isn't right. What have I forgotten?
You found that it's product,
So I did the derivative of the first, but I missed what? Times the second. So there should be an x here. And then minus the first times the derivative of the second. So I did the derivative right, but then I forgot to write the second. Okay, equals. Now we got the right-hand side. What do we got? Derivative of e to the something. E to the something. But then times the derivative of the interior. And what's the interior? A product. So we're going to do the e to the xy times the derivative of the interior function, which is a product, so times the product rule, right? So we're going to do derivative of the first, 1, times the second, y, what, plus, that's times, plus, the first times the derivative of the second. Times y. 1 times y. And this is y prime. And that's the bracket. Does it make sense? Any questions? So I'm applying all the same rules as before. Anytime I have a y, I have to consider that it's, if it's just y, it'll be y prime, but if it's y, a function of y, then I'm going to use the chain rule, because we have to think of y as a function of x. Okay, so now, how many terms are there in this entire equation? This is why I spaced it out, because what I see is that students will cram all the multiplication and plus and minus together, and then they have no idea where the terms are separated out. That's why I put space, because terms are separated out by minuses and pluses. Minuses and pluses. So put space between your minuses and pluses. It's going to really help. So you can now look at this and say, how many terms does this have? Or will it have once we multiply out, right? So we're going to distribute. Distribute, and then after that, how many terms will I have? Total on the left and right. I heard 4 on the left, 2 on the right. Agree? Yep. 4 on the left, 2 on the right, and what do we say? We want to, what are we after? We're trying to solve for what? What do we want? We want the rate of change function, right? The rate of change, and that's y prime, right? Y prime is dy dx. So we want to get some expression of dy dx, and it'll be a function of points. It'll be a function of ordered pairs, right? X and y. Okay, so how do I do that? I'm going to take all the terms that are going to have a y prime and get them to the left. And all the terms that don't have a y prime, get them to the right side of the equals. Okay, so which ones are going to have, we'll do blue for left and red for right, okay? So this is going to be what? That times that is going to be on the right. So it should be red. Red for right. There's, all right. This times this is going to have a y prime. It's going to stay on the left. Okay. This will stay on the left. This is going to go over to the right. This is going to stay on the right. And then this last one multiplied is going to go back to the left. All right, so the ones on the left are going to be my ones with y prime. So can I multiply these out and move them at the same time? Is it okay? First one that's going to go stay on the left is going to be negative 75 cosine x minus y times y prime. That's me just distributing that 75 cosine to the y prime. This minus 6y y prime x is going to stay on the left. What else is going to be on the left? E to the xy times xy prime, but that'll be minus because I'm going to move it over here, so it's going to be minus. And then, what's going over to the right side? All the rest of them that don't have the y prime. 75 cosine x minus y, but that will be minus as it moves over, right? That will be minus as it moves over. Next one. This one is going to move over, but it'll be plus when it moves over. 3y squared. And then finally right here, it will stay here on the right. E to the xy y. Okay, I'll pause and see if, did you follow this algebra? Anybody have a question? Did I lose you somewhere? What are we after? We're after the derivative. In local areas, the rate of change of y with respect to x, we know that's going to be a function of pairs of values, x and y, right? So it's going to be an equation that has x and y in it. And so we need to solve this, that first thing I wrote for y prime, which means move every term with a y prime to the left, every term without a y prime to the right. And that's what I just did. Then what are we going to do? We're going to factor out y prime. So we're going to have y prime times term 1 minus term 2 minus term 3. I'm not going to rewrite them. Equals that. So that the next step I'm going to write in the box. I'm going to write the answer in the box. So this step is now factoring out y prime. And to solve for y prime, we're going to do what? Divide, right? We're going to divide by, this is multiplies, we're going to divide by everything in this bracket. So in the numerator here, we're going to have this right side. And the denominator is going to be what's in that bracket, which is what I get from here when I factor out the y prime. So it's going to be negative 75 cosine x minus y. That's right. Okay. And then minus 6yx. So get from here when I factor out y prime, and then minus e to the xy times x. And we got it. Six terms, 3 had y prime, so I moved those to the left, 3 did not, so I moved them to the right, and then I got my rate of change equation. So what does this do for us? So here's a point pretty close to 2, negative 2. Not quite, but pretty close to 2, negative 2. It's actually 1.9, negative 1.8. If I were to take that x and y value and put it into this equation, what do you think I would get? What do you think I would get? And what do you think that is? What do you think? You're nodding. What do you think? What are you going to get? What number? Predict. -2. 5. 1/4. Yeah, people are saying, okay, good. People are saying 1. You should be thinking about 1. Why? Because if we were to zoom in here and look at a small change in x and the resulting change in y, they would be, the change in y would be about the same as the change in x that you picked. For a small change in x, you're going to get the change in y is going to be about the same. Therefore, that's a rate of change of +1. If we plugged in this ordered pair right here. Takes too much time. We could put that into GC up there, and we could do that, but we don't need to take time to do that. We could show that it's going to be just about 1. I'll zoom in. Yeah, pretty dang close to 1. Okay. Any questions on this? So this is pretty much as hard as they get. So that ones will be easier than this. It'll be less algebra intensive. But if you understand everything that I did there, then the easier ones should be fine. Should be able to do those. In the web work, there's lots of real basic ones to get you practice on. Okay, in the web work. So those, and like I said, those are all extra credit. Questions on this example, or the meaning of what we found? Okay, so we'll move on to some applications of a variation on this, right? So let's look at a falling ladder. There's also that, you see that there's a red, that's a ladder actually up against the wall, and there's a tricky monkey right there, and he's going to kick that ladder out and make it fall. Boom. And he'll never get tired of doing that. He loves to kick that ladder. Okay, so 10-foot ladder, it's flat against the wall, so it falls as shown. How fast is y, the distance from the top of the floor, changing with respect to x, the distance to the wall? So if I just pause it here, they defined a variable y there. What is the variable y? Can you see it in the picture? What it would be? But so, okay, right now it's about 6, but from where to where, right? From where to where is this variable y? It's all in there. Yeah, okay, so yeah, y is the distance from the floor to the top of the ladder. Variable or parameter? Variable, right? The ladder slides down. Y is going to do what? It's going to change. Specifically, how will it change? Decrease, right? It'll decrease. It starts at 10 and will decrease to 0. Likewise, x. Variable or parameter? Also variable. After the monkey kicks the ladder, that value of x is going to increase. It's a variable. All right? The length of the ladder is fixed, right? It stays 10 feet. Okay, so we're interested in what? How fast is the distance from the top of the floor changing with respect to x? What are they asking for? The rate of change of y with respect to x. Okay? So this is an application, actually an application of the stuff we've just been talking about. Can you finish the problem? Can you find the rate of change of y with respect to x, or in other words, dy dx? Can you do it? Take a minute. See if you can make progress on that in a minute. So here's a hint. Having y as a function of x is not the most convenient way to do this. That's a hint. Use what we've just been learning instead. Instead of writing y equals a thing with a bunch of x's, right? A function of x. Use what we've just been learning. Okay, so we already talked about how we can represent the quantity being asked for, right, as dy dx or y prime. Okay? In order to get that, my hint was we don't want to write y equals a function of x, so what else is there that's going to allow us to work towards dy dx? Where's Dimitri? How about Alec? Pantepa?
You use Pythagorean theorem.
Okay, tell me. Okay, good. So what he said was, in general, is we need an equation of x and y, right? So these examples we've done with implicit differentiation, we started with a relationship of x and y. Here, we didn't have that. So it's up to you to know that you need that and come up with it. So I'm going to do it without the square root, okay? The square root is going to, with our derivatives, it's going to make things complicated. So without the square root, it's a lot friendlier. So this is what we need first. The relationship between x, y, and 10, even as x, y change, right? As x and y change, that will always hold, right? For that triangle, for this triangle. And for that triangle. Okay, so no matter what x and y are, as they change together, this remains true, right? X squared plus y squared equals 10 squared. We just, for a whole family of triangles here as that ladder slides down. So how are we going to get dy dx? Where is Brandon? Is Brandon here? Surprise. Ivan. Ziyu, Wang. Crystal. What's you? Where? Raise your hand so I know who you are. There you are. How am I going to get dy dx? What am I going to do with this equation to get dy dx? What can I do? Not sure? Okay, how about Crystal? What's that? What have we done in the last examples to get dy dx from an equation of x and y? What did we do? What's that? Right, implicit differentiation. So let's do it. X squared. So what's the derivative of x squared? 2x plus 2y? 2y prime equals 0. Okay? So this is what we get. So starting with that equation of x and y, we implicitly take the derivative, and we get this, and we're going to solve for y prime, which gets us negative x over y. Negative x over y is what? The rate of change of the height with respect to x, the distance of the bottom of the ladder from the wall. Okay? How fast is the top of the ladder falling when it's 8 feet above the ground and 3.5 feet above the ground? And I should say, with respect to x. With respect to x. How fast is the top of the ladder falling with respect to x when it's 8 feet above the ground and 3.5 feet above the ground? Go. Those are two different questions. Two different questions. So I'll show the first question here. Oh, jeez. Doesn't like that. Where's Keenan? How'd this go? Did you get started? So I want to, when the ladder is 8 feet above the ground, the top of the ladder, I want to know how fast it's falling with respect to x. So what did you think about that? Negative x over 8? Okay, good. So you identified that the value they're giving you is 8. And we want to know dy dx. So the question is, what is x? What do we put over 8? Negative what? Where is Yui Zhao? Not here. Gone. Sean, Hullum. Nice. Okay. So the relationship between y and x is always this. So we can take that 8, put it in for y, and solve for x, because we know this is always true as x and y change together. So we get x squared plus 64 equals 10. I think x equals 100. So x is 6. Is that right? So we get negative 6 over 8, or negative 0.75. What are the units on that? Negative 7.75 what? A little change in x indicating how much y is going to change. So it's going to be feet per feet. And they don't go away. Why? Because they're in different directions, right? One is an x change in feet, the other is a y change in feet. So those are not really the same in space. So we got to leave it feet per feet. We know it for a change of for a change in x of some small number of feet. What's y going to do? How is the ladder falling with respect to x right now? Yes, right. So however much x changed, if x changed a little bit from this point right here that I'm showing, y would come down 3/4 as much as x changed, right? 3/4 as much as x changed. That's what that's saying. All right, did anyone do it for 3.5? What'd you get for the final answer? So you go through the same process. Did you get a final answer for that? Okay. Anybody? Yeah. So that's perfectly legitimate to have expressions as answers. That's great. But for analysis sake, did anyone solve the actual the number? Yeah. 2.7. Anybody else get that? Good. Okay. Feet per feet. What does that tell us about the rate of change? So when it was 8 foot, the rate of change was negative 3/4. And then down here, when we're at 3.5, the rate of change is negative 2.7 feet per feet. So for the same small change in x, what can you say about the second situation compared to the first? What does it mean that the rate, what used to be negative 3/4 and now it's negative 2.7? What does that mean about the ladder in this situation? Right. So faster with respect to x, right? For a small change in x, by the time it gets to 3.5 feet above the ground, you're going to see a lot larger change in y. It's coming down more for that same change in x as it's falling, right? So as it's falling, changes in y are increasing for the same change in x. Okay, questions on this? So that's a little application of what we were doing in the earlier problems. Now I want to change this up a little bit before I go on. Anybody have a question? Okay, so this expression gives the rate of change of y with respect to x, or how fast the top falls to the bottom, moving in feet per feet. In feet per feet. So it's a change in y with respect to change in x. Okay? But there's a different kind. There's a more common type of how fast, right? That would be how y, the height is changing with respect to what? A more common way of thinking about how fast something's changing, a distance is changing. Time, right? Okay. So how fast is the top of the ladder falling in feet per second, right? So this would be an important question to ask. Or the speed of the top of the ladder with respect to time. So we need this third quantity in the background now that we haven't considered yet, and that's time. So now time is going to be involved. And so if the bottom, we're going to consider that the bottom of that ladder was sliding out at a constant speed. That's going to be v. Okay? So the speed of the bottom of the ladder is constant, and now we're interested in analyzing how fast the top of the ladder is falling down. So if the bottom is sliding out at a constant speed, then dx dt is v. Dx dt. So how fast x changes with respect to time is this constant speed v. That should be easy. Makes sense? So now we start back with our original equation, but now instead of wanting dy dx, we want dy dt. So we're going to still do implicit differentiation, but no longer with respect to x, but with respect to t. So now everything is chain rule. Everything that we do is going to be chain rule. Because why? Because x is a function of t, and y is a function of t. And both of those are squared. So those are both, with respect to t, these are both composite functions. This is a function of t, and that whole thing is squared. This is a function of t, and that whole thing is squared. So every time we take a derivative, now we have the chain rule. Does it make sense? So what's that first one? Derivative of x squared will be 2x times the rate of change of x with respect to t, which is either dx dt or v. Those are the same, right? And then same thing, derivative of y squared will be 2y times, no, not v now. So the top of the ladder is not falling at a constant speed, right? So it's whatever dy dt is. So we have 2x dx dt plus 2y dy dt equals 0. So when we're doing this implicit differentiation with respect to time, everything you do involves the chain rule. Okay? And what were we interested in? We want to solve for what? dy dt. We want to know how fast is the top of the ladder falling. That's dy dt. So we're going to change things around here. When we solve that, we get the same thing we had before, negative xy, but then also times dx dt. We solve that equation above for dy dt. So look, so this is an equation, what? It has two rates in it. It's the first time we've seen this. Two rates in the same equation. So it's an equation that's relating rates, relating more than one rate, right? So we call it a related rates equation. It's bringing together more than one rate into a relationship. And what was the source of that equation? Where did it initially come from? Where did we get that? Where did we start to get that related rates equation? This is the key for solving these problems that we're going to do. Where does a related rates equation come from? Initially. What do you think? Where's Ashley? Roman? Ashley here? So where did this is our related rates equation. Where did we start to get to this, right? So where did this equation come from initially? What's that? So let me give you some choices here. 1, 2, 3, or 4. Where did the related rates equation come from? 1, 2, 3, or 4? Initially. 3, good, right. Right? It comes from what? The equation that related the original quantities, right? So we had dy dt, its accumulation quantity is y, right? Dx dt, its accumulation quantity is x. So the related rates equation came from the relationship of y and x, the accumulation quantities for which we have the rates, right? In the related rates equation. So this is the key. To get the related rates equation, you first have to have the equation that relates the quantities for those rates, the one that I put a circle around. So with optimization problems, what was the key to those? All of those were involved what? Optimization. Please get it right today. A function. What function? Function, two variables, and tell me about one of those variables. The The dependent variable is what? What we're trying to optimize, right? A function whose output or dependent variable, like the y, is that quantity that we want the most of or the least of. Here's the big takeaway for related rates problems. To get this related rates equation, we're always going to start with building the equation of the associated quantities. So what do we relate? We related dy dt and dx dt. So we need an equation of y and x. And that was our Pythagorean theorem in this problem. X squared plus y squared equals 100. And then from there, we know we're going to differentiate implicitly with respect to t, and that's going to get us the related rates equation. And then we'll read the problem carefully to find out what they're wanting from us. But this is the key to it. So let's do an example. The edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? So let me give you a roadmap here. So this is the in a nutshell. This is how the solutions is going to go. We got to identify the rates and the quantities for which we have rates, and build a quantities equation. Okay, so a more detailed version is, let's start by identifying the rates. What are all the rates associated with this question? What are all the rates of change that we have? What's one of them? Okay, nice. So he said that 2 centimeters per second. You should identify that as a rate, and particularly, that's the rate at which the edge size is increasing. Okay, there's another rate. Where's Jorge Campos? Here? How about Ratsko? Here? Aswathi. So, is there another rate that this problem mentions? We got the first one of 2 centimeters per second. Is there another rate mentioned in this question? And what is it? Don't know. Not sure. Okay. Where's Amanda? What do you think? Yeah. So it says how fast is the volume changing, right? It's indicating that we want to know how fast the volume is changing. So we have two rates we're talking about here. So how fast the edge length is changing, how fast the volume is changing. So when we identify them, some of them we may know the value of, and others we won't. Okay? And that's the case here. We know how fast the edge length is changing. It's 2. We don't know how fast the volume is changing, but that's what they want us to find. Okay? So then, if we know the basic gist of this is to have the quantities equation, then we're going to identify the quantities associated with these rates. This is the easiest part. So what's the quantity associated with the rate of change of edge length? What's the quantity associated with rate of change of edge length? What is the quantity associated with rate of change of edge length? Where's Nathan? No, I'm not asking for a value. I'm asking for the quantity that's associated with rate of change of edge length. That's still a value. Just want to know what quantity is associated with rate of change. Hint, it's the easiest question I'm going to probably ask all semester. What's the quantity associated with rate of change of edge length? Say it. You just said it. Just say it again. Edge length. Edge length. The quantity associated with the rate of change of edge length is the edge length. Okay? You all get this one. What's the quantity associated with the rate of change of volume? Volume. So let's call edge length S, and we'll call volume V. So we're going to define our variables here. Edge length is going to be S, and volume V. So now we've identified the rates, we've identified the quantities, and now we're ready to what? Build the quantities equation. So the quantities equation is the relationship between edge length and volume, in this case, of a cube. What relationship brings together edge length and volume of a cube? I know Ian knows. Yeah. The edge length cubed, right? So we're going to write, so now we're ready to write the equation that relates to quantities, and that's going to be, oh, bad notation. Volume equals S cubed, okay? Volume equals S cubed. And how am I going to, so that's the equation that relates to quantities. Now I want the related rates equation. So I want the quantity that relates the associated rates. How am I going to get that? Where's Richard Givens? Randy. How am I going to, I've got V equals S cubed. That's the quantities equation. How do I get the related rates equation? So basically, it's going to relate what? dV dt and ds dt. Where's that going to come from? Not sure. Where's Jason Fox? Jason here? Jason. I've got V equals S cubed. How am I going to get the related rates equation, or the equation that relates dV dt and ds dt? Not sure? Volunteer. How am I going to get that? Yeah. Right, so he's going into more detail, but you're going to take the implicitly differentiate with respect to t. We're going to do our implicit differentiation with respect to t. And so on the left, it's going to be derivative of v. It's v, so it'll be the derivative of v with respect to t. And then on the right, we'll have chain rule, right? What will the derivative be on the right? 3s squared ds dt. So we're going to take the derivative of v with respect to t and s cubed with respect to t. And that's going to give us dv dt equals 3s squared ds dt. There's our related rates equation, right? So again, related quantities, related rates. So it's something of a circle. My suggestion for approaching these problems is somewhat of a circle. You're going to start by identifying the rates, and then you're going to work your way to getting the related rates equation. And that's, so we're going to go the rates, the quantities, the quantity equation, then take the derivative, and you get the rates equation, and you're back where we started, focusing on the rates again. So, what is it asking for? How fast is the volume changing when each edge is 50 centimeters? So, we're interested in knowing what? Which of these things? So we actually have three different variables here. dV dt is variable, s is variable, ds dt. Which of those are we interested in knowing? dV dt is the unknown, and that equals 3 times. So we want to know how fast the volume is changing when the edge length is 50. So that's our value of s, right? And what's ds dt? 2. Right? So the edge length of 50 was given. The rate of change of ds dt was given. so that gives me my dv dt. 6 times 2,500, or was it 15,000. What are the units on that going to be? Centimeters cubed per second, right? dv dt is going to show us the centimeters cubed per second. What if I plugged in this 50 here? So I know that S is 50, so V equals 50 cubed. Is that a good idea? And what would happen? And what would happen in the rate of change equation? If I plugged in S equals 50 and solved this thing out. Yeah, what would you get in the right? The derivative would be 0. So that would be assuming that the volume, that the side length isn't changing, right? S is a variable. So it's got to stay a variable all the way through the process until the very end, okay? If you put S equals, this is, I'm bringing this up because it's a common mistake the students make. If you put the 50 in this V equals S cubed, then basically what you're saying is that the cube isn't changing. It just always has a side length of 50. Okay? And its volume is fixed. So therefore, how fast is the volume changing? 0, right? 0 centimeters cubed per second. And that would come out in the math because you get the right side to be 0 when you take the derivative. So make sure variables stay as variables until the very end when you're ready to replace them with the current value of the variable. Okay? If you replace it too early, then you're saying that that is not variable but constant, and your derivative will be 0. Okay, questions on this example? Okay, so I want to we'll look at that one if we have time. Let's look at this one. This one. Look at this one. So a motorboat leaves the shore going 28 kilometers per hour in a circular arc with a radius of 60 meters. How fast is the boat's distance from the shore changing when the boat has traveled a distance of 150 meters around the circle? Okay, so remember what our strategy will be for this. In a nutshell, the strategy will be well, that finding the rates is kind of what do you mean by find? Do you mean okay? So you're sorry. Okay, so you want to identify what rates are involved. Okay, so yep. What's our strategy? Identify the rates. So this is the what? This is the solution in a nutshell. We want to get an equation that relates the important quantities, from which we're going to get the related rates equation. Okay? That's the solution in a nutshell. So then the more to get there, we're going to start by identifying the rates involved. Then we're going to assign notation variables for the quantities and rates. This was before it was identify the associated quantities, right? And then from the quantities, build the quantities equation and write the related rates equation. All right, so let's let you try for a couple minutes here and see what you can come up with. See how much you can do. And we'll walk around and help you. You're either making progress or you're getting help. Those are your options. Okay, so I better move here for time's sake. So, identify the rates. 28 kilometers per hour is the rate. What rate is that? It's the rate of change of the distance traveled by the boat around the arc. Okay, so I called that distance traveled capital D. So the quantity is capital D, the distance traveled by the boat. So dd dt is that 28 kilometers per hour. Make sense? So the rate of change is the speed of the boat, and the associated quantity is the distance the boat has traveled around the arc. That's the associated quantity. I'm calling that capital D. Okay? The other rate is the rate of change, how fast the distance from the shore is changing. So the associated quantity is distance to the shore. That I'm calling y. So I'm calling y equals the boat's distance to the shore. Its rate of change, dy dt. So what do we need? We need an equation that relates y and d. Where's that going to come from? I need an equation that relates that distance to the shore and the arc length. Okay, I think he's onto something there. It's going to be trig, right? It's going to be trig. So consider the center of the circle here. What does capital D relate to in this circle? What does it relate to? It is the distance around the arc. But if we're going to use trig, then what is distance around the arc is essentially the same as angle measure, right? Angle measure. If we measured this distance in radius lengths, how long would this distance be in radius lengths? It would be theta. It would be whatever this angle is, right? So what is d? D is, if the radius is 60, it's going to be 60 times, not sine theta, 60 times theta. Okay, why? Because theta is that arc length, whatever the arc length is. It's basically it's d measured in the unit of the radius. Okay, so if we want that distance d, we would just take the number of radius lengths times how long each radius is, right? The number of radius lengths to get from there to there times the length of each radius is going to give us d in terms of meters, kilometers. Okay? And so that's going to be important. What about y? What is y? If it was measured in radius lengths, right? So if we measured that y in radius lengths, it would be sine of theta, but we want to measure it in kilometers. How do we do that? Times it by 60. So in radius lengths, it's sine of theta. In kilometers, it's 60 sine theta. So now, what did I need? I need an equation that relates y and d. So I basically, how do I get an equation that relates y and d out of these two equations? Well, I can make theta equal d over 60, right? And if theta is d over 60, then I can replace it there, and then I get y equals 60 times sine of d over 60. So there's my quantities equation. I've just related the distance d with the distance y. Got my equation that relates y and d. Any questions on that? Maybe that's the hardest part of the problem, is coming up with that. But which is really about knowing what is that d? Well, if d were measured in radius lengths, it would be theta. But if we want it in kilometers, then we're just going to take the number of radius lengths, theta, times the kilometers of each radius length. So d equals 60 theta. The same argument here for that, and then we put those two together, and we got y equals 60 sine. And so now we're going to do our related rates equation, which means take the derivative with respect to t. So we're going to get dy dt equals, what's the derivative of sine? Cosine. By the chain rule, I need derivative of d over 60 is? No, this is just a constant. It's a constant times d. So it's going to be 1/60th, and then by the chain rule, times dd dt. And what do we want to know? We want to know dy dt. What is capital D at the moment? 150. What's dd dt? 28. We got everything we need to crank out what dy dt is. I'll leave it up if you want to ask me about it on the way out.